gets onto the stage by switching on his video, unmuting his audio, I will like to introduce Dr. Rob to the audience. Dr. Rob is an ARM fellow responsible for technology direction at ARM Research. He works on a variety of topics, including distributed systems, low power design, technology road mapping, and next generation memories. He has worked on 15 plus Moore's Law note, has published 100 technical papers, and has 40 US patents. Dr. Atkins joined ARM as part of its acquisition of Artisan Components in 2004. And prior to Artisan, he worked at Agilent and HP. He holds a PhD from McGill University in Canada. And Dr. Atkins is IEEE fellow and serves on a number of conference and workshop committees. I have had the privilege of hearing him in DAC and ITC, and I look forward to his talk here. Dr. Rob, over to you.
Thank you, Naveed. Let me see if this works. It's always fun to see what happens. There we go. This is looking promising. Come on, you can do it. There we go. All right, do you see the slideshow?
Yes.
Is there a weird window in it, or does it look good?
We see it clear.
Perfect. Okay, let's go with that then. All right, so we heard from Dr. Shivaram's talk that you should question anybody who says Moore's Law is slowing down, so I assume you'll be getting your questions ready for me. But I'm going to talk about logic in particular rather than necessarily NAND or other forms of memory. And in particular, what I'm going to talk about is how we can use 3D integration to advance Moore's Law and move it forward. So going up rather than shrinking is the way of the future. Let's see, for some reason that didn't work. There we go. Okay. One way I've found that's convenient to visualize Moore's Law is taking a look at the balance of processes that are being built at TSMC. So they are kind enough to put this in their financial statements every month. And you can see a couple of things that are interesting. First of all, for years, up until 65-ish nanometer, everything kept ramping every couple of years. Things started to slow down, and from 16 nanometer to 7 nanometer was approximately 4 years. There was a sort of intermediate half node at 10 nanometer that was put in as a stopgap, and you can see it ramped up and ran down. So this gives you kind of an insight into how Moore's Law is proceeding at the moment, and essentially you can see that there's some slowing in it. It's also, I think, useful in these discussions to look back at Moore's paper. So we're often used to seeing the figure on the right. So that's the one where things double every couple of years. But the figure on the left, which is figure 1 in Moore's paper, is also, I think, instructive. So if you look at the blue arrow going down and to the right, then you can see that over time, the optimal density point changes. So it's not just that the number of devices you can squeeze on a chip increases, it's that the number of devices you can squeeze on a chip at a reasonable cost also increases. At any point in time, you can use the red line, so you can essentially put more transistors down, but they start to cost more. So a lot of times when we see things now that say, oh, Moore's Law isn't shrinking or isn't slowing because I can do X, Y, and Z, what you're actually looking at is the red arrow. And so it's instructive, I think, to look at what Moore actually said. He said that he expected the slowing down to eventually, or that Moore's Law would eventually slow down and would be replaced by some sort of alternate system construction methodology. And that's kind of what we see. I took a look at what was in the Vision Summit list of topics. And if we look at all 10 of those topics, we can see that many of them, probably 6 or 7 of them, directly require Moore's Law to go forward, and some of the others as well, too. So Moore's Law impacts everything. It's driven progress everywhere. But what happens if it can't do that anymore? What happens if it slows, or what happens if it stops? Effectively, we can scale up or we can scale out. So if you look at, say, the Mumbai skyline, you can see that it's scaling up. There's more and more tall buildings there, and they add new ones every year. On the other hand, if you look at scaling out, Bangalore, I think, is a great example of that. In the years that I've been going there, it's grown immensely. Almost everything in this picture, for example, outside of the office, the ARM office, is new. That most of those buildings, in fact, possibly all of those buildings, weren't there a decade ago. And it's really exciting to see the scaling out aspect of the city. This occurs in silicon as well. We can start stacking things on top of each other, or we can build wafer scale systems, or we could do both at the same time. And those are really, I think, the two directions that Moore's law goes after transistors stop or slow down their scaling. So if I tell you about stacked die, then you may, if you've been around this industry for more than 10 years, say, wait a minute, that already happened. People talked about that, TSVs, a decade ago, and mostly it didn't go anywhere. Dr. Shivaram actually showed you vertical NAND, which is one example of where it did go somewhere. So his 112-story NAND devices, those things exist. Similarly, there's 3D image sensors of various kinds, but for logic and memory, or DRAM or SRAM type memory, it mostly didn't happen. And that was due essentially to two things. The manufacturing cost and complexity of building a stacked object was actually more expensive than just waiting for Moore's law and getting the same density increase for free. There's also a design cost and complexity piece that if you don't have EDA tools to support building one of these things, it's just not going to work. So even though the picture on the right there, which is from an IEDM paper back in 2013, that's still an ideal kind of a structure with all sorts of heterogeneous things stacked up together. The reality is that outside of a few specialized cases, it didn't really happen. The next effort at chiplets, essentially building, happened in the last few years, and it's a result of two different things. So first of all, data center workloads, as again we heard in the previous talk, they're scaling up immensely, and they don't show any sign of slowing down. But Moore's law is already slowing down from the perspective of large CPU or other complicated logic chips. When that happens, you have essentially two things happen. The chips keep getting bigger and bigger, and eventually you get to the point where building it on smaller chips and putting them together in a package or on a substrate of some kind is actually cheaper than one big one. You can see why in the stylized picture here. So if we build a wafer and it's covered with tiny chips like the one on the right, when we spatter some defects on there, all those little black dots are no longer functional chips, but still 90% plus of those chips work. On the other hand, that same defect pattern on the bigger chips knocks out 8 of the 24. So that's only 2/3 yield. So eventually the yield hit from adding or from making chips so big limits your production, even before you get to the reticle size. When you start stacking chips or building multiple chips for a system, you can actually do some additional optimization. So you could, for example, put your analog in an older node or your high-speed digital in a leading edge node and so on. So there's a lot of benefits to doing this level of scaling as well. But I'm going to talk even beyond that about where we can go next. And to see where we're going, again, the previous talk introduced this well. The industry, by and large, is wired for 2D. When I design things, or when you design things perhaps as well, I tend to think in block diagrams, and block diagrams are inherently a two-dimensional construct. Similarly, all our tools are designed around a 2D implementation. We look at them on a 2D screen. And even something as complicated as putting chiplets on an interposer, it's 3D-ish. It's often called 2.5D, but I think it's realistically 2.1D. And the reason why I think that is when you take 2D objects and stack them up, you don't really get 3D. And to show you why that is, I took a picture of the spaghetti maker. If you look at the spaghetti maker, there are a bunch of strands coming out of that spaghetti machine, and you could take those strands and you could twist them arbitrarily. So you could make out of, say, n strands of spaghetti, you could make n factorial different combinations of twists on them. There's no way that you can do that in any of our 3D technology. Even with 112 layers, it's not enough to arbitrarily reorder any 3D pattern of wires. So it, it creates some opportunities, but they are still limited. But a key point, I think, is that because we're so wired for 2D, we haven't really thought of everything that we can do in 3D. So even with the simple structures that I'm going to talk about, there's a lot of potential advancement. Another thing to think about is energy. And again, the previous talk talked about this a little bit. If I have 100 picojoules of energy, I could run a microcontroller for 10 cycles. Or I could do 300 Mac operations in a machine learning accelerator. I could write some memory, about 300 bits of DRAM or SRAM. I could send 5 bits across an LPDDR4 interface, write a bit of flash. And when I start going wireless, then I start really chewing up the energy. So I can only transmit, it takes 1,000 times 100 picojoules to transmit 1 bit of 5G data. And effectively, what we see from this is that it's much, much more efficient to process data locally than it is to move it around. And that's, again, the storage class memory question, computed memory question, all of these things, it's really pointing to the challenge of moving data around and the desirability of not doing that. The specific piece that matters is the memory system and data transport versus compute. So again, talked about that a little bit before, so we don't have to go into a lot of detail, but just basically moving things is expensive. There's also a scale issue. And this is, I think, worth thinking about because the scales of what you're doing change dramatically. So if I have a few rocks to move around, I can use my shovel and wheelbarrow. If I have a much bigger set of rocks, I probably want to move to the excavators that are shown in the middle picture. And if I want to move a mountain, then the excavators aren't really going to help either. I need some other technology. So it's not just the data transport that's the issue. It's also the how much data is being transported in any given situation. Okay, so if we think about the existing memory system, if we sort of map it to human scale, from a CPU-centric view, the registers are kind of like a book. I have a book on my desk, I can look at it, and I can learn something. The cache is more like the bookshelf near my desk. I'd have to actually get up, walk over to it, and bring it back, but it wouldn't take very long. DRAM, on the other hand, is more like the library. So for a CPU, it's effectively, it has to stop doing what it's doing, go to the library, pick some book off the shelf, and bring it back. And so you typically want to bring a few books back, but it's a very slow process. And when you start going to flash, you can move huge amounts of data, as the container ship shows, but it's a very, very slow process. And then when you go to the cloud, it's kind of like a sailing ship. It'll get there sometime. You're not really sure when. So the time, because the time scales on the machines are sub-nanosecond in the CPU world, the delays of going off chip to flash are very significant. So we want to try to stack some of these things up. And again, Dr. Shivaram referred to this previously in his talk. But it's interesting when you start thinking about vertical connections, when you start looking at tall buildings, the height of a building is not really limited by construction technology. It's really limited by elevators. So if you look in the picture on the left is sort of a mid-level floor in the New World Trade Center in New York. And you can see that the elevators, the heat and air conditioning, and so on, the other miscellaneous overhead in the building starts to consume pretty close to half of the overall area of that floor. And that's the limiter. If you built the building 200 stories tall, that footprint would grow. It's effectively Rent's rule for buildings. So that brings us to a multi-die system. If we're going to build one, what are we going to do? What are we going to put on each layer? In theory, you can split logic across different layers. And so if you stack 2 die, the longest single path is now square root of 2, 1 over square root of 2, so 30% smaller. In practice, the elevator overhead starts adding up, and the complexity of doing that increases as well. So that's a theoretical possibility, but at the moment it's not really viable. On the other hand, stacking multiple cores up and using some kind of 3D interconnect, that's definitely in the realms of possibility. We have to choose whether we're going to be coherent or non-coherent. We have to choose if we're going to use just a wire connection or build a PHY of some kind. And there's a lot of open questions and a lot of research being done in this area. Effectively, I think from where we can see benefits, moving an L1 to a different layer, it's probably not enough density in the interconnect at the moment. L2, probably it's too slow. Even though it's vertically adjacent, it's probably still got too much overhead. L3, on the other hand, that's getting interesting. System level cache is very interesting. And when we go to other memory technologies, that's cool too, but we need to understand, again, the cost, complexity, and logistics, especially when the DRAM and flash are often made by different companies than make the logic. We also have to manage heat, power density, test, debug, and so on. The picture on the right is a test chip that we made. It shows we built about 3,000 3D connections between two face-to-face die in this ARM Global Foundries partnership. We've got the die back, they work. It's pretty cool. You'll expect to hear some more about that coming up. So let's look at a canonical system here. So let's split it up. So we'll put system level cache in one tile, and we'll put CPUs in another tile. We're going to build it around a high performance coherent mesh network. So that's what the XPs are, they're cross points in the network. One way to do this would be to put big CPU cores. So this would be sort of A75 in ARM terminology or similar things in anybody else's CPUs. Those would definitely be on a leading edge process, so 7 nanometer or 5 nanometer. The SLC tile, on the other hand, in addition to system level cache SRAM, would also contain the NOC control, probably some little CPU cores, so A53 or A55 class, and it could be one process node back. There again, there's a lot of interesting details on how you put these things together and what you might expect with them, but effectively, you can build a system like this in today's technology. You can do some interesting things with it. We could add additional layers of accelerators. Where exactly you put the I/O depends on the package. How exactly you deal with thermal also depends on the system and so on. But at kind of the block diagram level, this is effectively what the system would look like. Now, with this kind of a system, it's expandable in different directions. So what we can do now is we can say, we could put more tiles on there. So we could build a bigger chiplet by just adding more of these tiles. And that allows us to size the object to meet whatever performance, thermal, yield considerations we have. That, again, it's a fairly complicated set of calculations that you would go through, but basically you'd want to think about how many operations, how many operations per second, what's the throughput that my system needs? How many CPUs does it take to do that? How many cross points in the memory should I have to consider, and so on. We could conceivably add multiple layers of system level cache. So that allows you, interestingly enough, to build a configurable system where, say, if we could, each time for each core, we added a few megabytes of cache with one layer. If we added two, we would double that. So for different applications, you could conceptually build from the exact same set of building blocks very different systems that would be much more difficult or even more challenging, possibly impossible to build in a flat technology. And then finally, once you've built these stacks, you can put them onto a substrate. So the picture on the right shows 4 of them with some high bandwidth memory around the side. And you're starting to get some very impressive performance. If you start adding more of these things, you can actually fairly quickly go from teraflop performance up into close to petaflop performance without adding that many of these objects. And because they're all in a small area, you save a lot of energy on data transport and movement, which means that you actually potentially use less power than you might in a board level solution. So again, there's lots of neat things that are going on here. That effectively moves us into a new world. So now if we're dealing with a system that looks like the one we just described, we can think of it as opening up lots of books at the same time, surrounding your desk with bookcases, moving your desk into the library so that you've got those left, then putting your whole library onto a container ship, and then sitting in a harbor with all these other ships. So we can, by physically concentrating the processing, the storage, the transport all together into the same, roughly same physical space, that allows us to improve the performance of our systems. It also allows us to move into applications like, cars or robots, where the physical size of an existing rack is a real limiter to the ability of the object to do as much processing as it's likely to need in order to be as autonomous as people would like them to be. So if you want to have self-driving cars, they're probably going to need something like this in as their processing element in order to do the calculations that are necessary. All right, so of all these 3D technologies of die stacking and flipping and folding and packaging and so on, it's very difficult to predict at the moment what's going to win. So what's going to be able to take the existing motherboard and put it onto a wafer or a stacked set of wafers, we're not entirely sure. There are a bunch of attempts that are out there. Some of them are going to succeed, some of them aren't. And we're reasonably confident that the hyperscalers of the world are going to come up with the winning solution first. Of the features of that these things will have, they will have a scalable modular design. They will have commercial EDA support. They're going to have heterogeneous compute systems on them. Whatever system it is will have to solve the memory bottleneck, which we alluded to in this talk, but didn't really go into a lot of detail. Same with the I/O bottleneck. And there are going to have to be answers on test, yield, debug, thermals, and all the rest of it that are really going to be critical to making these things work in practice. So that's sort of a brief overview of where we're at, and I would be happy to answer any questions. So thanks for your time.
Thank you, Rob. That was pretty interesting. It connected to the previous talk and something that all of us are talking in any event, conference, or strategies that we go about the chiplet. There are a couple of questions, and let me pick up a couple of them. So I think as we see this progress, I'm sure there will be very soon third-party chiplets that will start coming in as well, right? And would that involve maybe a standard that we need to think about for integration and the overall logistics that will come in to go and include those?
That's an excellent question, and I think there's a market impetus to have third-party chiplets. There's also, on the part of the people who are manufacturing chips now, there's a desire to not have it. Because if you could have both halves of the system, that's better than having one half. So the people who are building them will be somewhat resistant. But you're right that if and when a true chiplet marketplace emerges, it's going to have standards for what the interconnects look like, where they're positioned, how they connect to other things. Essentially the same kinds of things that JEDEC does now in memory will have to start happening in logic. So yeah, it's potentially quite exciting. Or alternately, the world could go to a Z-glue kind of thing where there's people who are professional integrators of other people's chiplets. So.
True. And another good question that I think we are talking about a lot of the silicon techniques from design to manufacturing, but what impacts will these innovations in packaging and stacking will have on OS like Linux to exploit these?
That's also a really interesting question, because if you look at the system that I just described, there's a question of where exactly what the programming model is for it, and then also what the abstraction level is for somebody programming the thing. Can they think about, I have an application that I want to run, and it will magically, through whatever OS exists or things built on top of other OSs, it'll distribute itself across all those cores and systems and I won't have to care? Or will it be like many existing chips where to actually get something that exploits it effectively, you have to know not only where everything is on every single chip, but you have to know the obscure interfaces and system calls and electrical signals that need to be raised to establish those connections. So there's definitely a lot of work in going from the current state of a software stack to the ideal future state where you could write an application and run it on anything, regardless of how it was actually implemented.
True, true. And then finally, maybe we'll have to find a term of saying what do we rename KGD, the known good die to known good chiplet, and then maybe a die and then beyond.
Yep. I always think they should be called known almost good die or mostly good die.
Absolutely. That was very engaging talk, Rob. Thank you so much for taking time out and sharing your thoughts as well as what you see ARM doing and some of the other ecosystem partners are doing. We appreciate your time and effort to do that. And on behalf of the whole IESA team, I would like to thank you. And here is a memento for you.
Oh, thank you very much.